Hey guys, we're going to talk about mass movements today. And as a part of that,
And today marks 50 years since the deadliest natural disaster in Virginia's history.
I wanted to just highlight that 50, well, I said 51 years now, was the anniversary of Hurricane Camille. So that was 1960, no, 52 years, 1969. And Nelson County was the site of a ton of rain. And not only rain, but also landslides. So the rain saturated into the ground, got the ground really, really saturated. Gravity did the rest. And so the question becomes, you know, why? I mean, we live in an area that's not prone to too many natural disasters. And we're not Nelson County, of course. We're up here in Shenandoah and Rockingham counties, but we have a lot of slopes around us. And of course, so that means that that mass movements are a major hazard for us to think about as well. You can look here. I would encourage you to go check out this YouTube video. I'm not going to spend time watching it here as part of this, but do go check it out on your own. You can also check this one. This one called "Living in Virginia: Remembering Hurricane Camille" goes through all of that. A number of people lost their lives in that event, and so it's a pretty traumatic one for the area. Mass movements. When we talk about these, we're talking about, yes, those are people down there. That's a rock. We're talking about situations where large volumes of earth are moved downslope. Ultimately, that's basically what it comes down to. We sometimes think of these as landslides. Landslide is a very general sort of everyday term that we'll just say common folk use. There's nothing wrong with landslides, of course, but the term landslide is too all encompassing. Whether it's a dry rock fall, kind of like this, or whether it's a slurry of mud, it's still a landslide. But if we talk about it, we can give them different kinds of terms that basically define them based on the amount of water involved, and that's really more useful to us. So, bottom line is gravity is transporting materials downslope, and so usually water and ice are not involved in necessarily the movement downslope itself. Gravity actually does that work. But gravity, the work of gravity, and I should say specifically the shear force that we're going to get into in a little bit, is really the critical thing. But water is involved. Water has to get the ground the wet and so forth. But so gravity, vibration, and water are of course involved here. And this is another video. You can go check it out. This is a video of a house toppling over in a landslide in Japan. Actually, I'll show you a little bit of it here. This is pretty cool. Ouch. 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 Yeah. Pretty nasty stuff, right? Well, gravity, of course, is constantly pulling materials down slope, um, even though they're opposed by friction. And so once gravity can overcome the friction, we're going to call the friction the shear strength, and gravity causing the motion of the material, the mass, the shear force. The steeper the slope, the greater proportion of full-on gravity you're working with here. But uh, vibration can help, of course, vibration from earthquakes and things, but also not just earthquakes, but like you build a road on the toe of a landslide, you have cars and trucks vibrating across that road all the time, and that causes a problem. So if we steepen a slope, of course, if we have a slope that's entirely flat and you have a rock sitting on it, that rock's not going to go anywhere unless somebody comes around and pushes it. You have to have somebody apply a force from one direction or another. If you increase the slope, so that's the slope is important, and then you lubricate it, or you not necessarily lubricate it, it's not really the right word for if you get the material underneath of it really, really wet so that it gives way, or the material itself wet so it gives way, then you can cause things to move. Of course, gravity is pulling it downward directly. You have the shear force trying to hold it to the slope, and then you've got the force that's parallel to the slope. That's the shear strength force, and then the shear force is what's pulling it down slope. And there's a number of variables involved with that, as you can look at in this week's homework. And here are some of them. There's a term that describes that we use that describes something called the safety factor. So if a landslide is going to develop or not, it's going to develop. We will calculate the safety factor, which is basically um, the uh, the ability for the material to resist moving versus it being, driving it down the slope. So the resistance forces, which is the shear strength forces, this arrow here, are then divided by the forces that represent D, the driving forces. And so there's a variety. There's actually a whole lot more forces, a whole lot more things involved with the driving forces here. But when the numerator is 1 and the denominator is 1, the safety factor will be 1, which means that if your safety factor for that particular potential landslide is a value of 1, it's balanced. It's on the edge of going, but it's not going. And likewise, if the driving forces are greater than the shear force is less than 1, you might have 10 here and 1,000 here. That thing's going. That thing's moving, right? There's a lot of things involved here: the density of the rock, the density of water itself, how thick the unit that has water in it is, that's saturated is, the thickness of the slide, the angle of friction, that's the angle of the slope, and so forth. A lot of variables involved there. So, there's been a lot of landslides. This is just one from Madison Canyon, 1959. Water gets involved. What water will tend to do is actually act outward on the grains that it's sitting in between, and will actually increase also the force of gravity. Actually, some of the driving forces. It's not as much a matter of you're loosening the cohesion of the sediment, but you're also adding mass because water has mass, and so those two things together, from enough water, might be enough to actually cause the whole thing to fail. But an important thing here, of course, is to think about slope. And certain materials will sit at a particular slope. If I dribble a pile of sand, and I'll try to do this in class, it's going to fit. It's going to hit what's called the angle of repose. So based on the moisture content of that sand, it's going to sit at a particular angle. And this is something I can easily demonstrate in class, which I'll do. But dry sand has an angle of repose of about 30 degrees. Water saturated sand doesn't have much of an angle of repose at all. But if it's just damp, it has a lot of cohesion. The water actually causes it to stick together. So some water is really, really good for helping increase the shear strength. If you get too much water, it can be a burden and increase the shear forces. It can be a glue or it can be a lubricant. That's because water has a very high surface tension. Okay. So as more water is added, and of course it creates a loss of cohesion over time as you overcome that surface tension factor, the capillary action, and so forth. You lose a sense of cohesion, but you also have now added all that extra mass that it could cause things to move down slope. Now that's for sand. So if you have different materials, they have different angles of repose and when dry. And of course, so angular pebbles have a different kind of have a different angle of repose than say fine sand. And so that, of course, that matters on your slide. Okay. So these are the different kinds of mass movements. Generally, it's a range of increasing slope angle this way, and then increasing water content and diminishing material coherence, which again is all related to water. So some of the slides are just big chunks of earth moving downhill in a kind of gooey fashion. Other things are like solifluction, just kind of sliding downhill very slowly. Depends on how much water is involved, and rock falls have almost no water involved in many cases. Avalanches are another kind of mass movement, just with snow. Now, we can do this. Of course, there's anthropogenic effects here that are involved. The oversteepening of slopes, road building, mining. These are all different things that can cause vibration, also different changes in water content that can affect cohesion and so forth. And make a potential slide even more potential than it was before by reducing the shear strength. Okay, and so natural oversteepening, for instance, is an example of that. These are some of the examples of natural oversteepening. Building a house where it shouldn't be. We have a lot of that around here. So I'm not going to get into the different types. I'm going to give this presentation to you. You have it. You can go through them. And there's also a USGS document that goes through that. What I do want to show you is this document. Okay, this is going to be your homework this week. You're going to be creating a spreadsheet that looks a lot like this one, right? And you're just going to be, this is the student version actually. So I give you the spreadsheet already. And so you use it with this in conjunction with this particular activity here to answer some questions. This should be listed as a Google Doc for you. This is a free body diagram that shows you the different forces involved here. And so F sub S here are your shear forces. All right, that's discussed up here. All right, and that's the shear stress. And then F sub n here is the normal stress, all right? But also we can look of it as the shear strength, all right? Or at least in part. It's in part the normal stress, but it's also the rest of these other things, cohesion and other properties. That's listed primarily over here. We've got the safety factor here, where you're looking at the this equation, and so you're going to be looking at these different variables and calculating the safety factor, which is in this case FS, factor of safety. And so that's essentially what you're doing. Now, this is going to be important to us because the week after with Mrs. Cluse, you're going to calculate the amount of work it was necessary for the landslide that was caused by the eruption of Mount St. Helens to move where it did. And so, and then compare it to something that makes sense to you. So be thinking about that. You're still gonna need your topographic profiles, for instance, at that point. But anyway, this is what you're doing next week. Well, you have a little bit of time in class to think about this, work on it, but we'll just go from there. All right, guys, that's it for today.